Good morning, everyone. I'm Rahat Bhatia, and today I'm going to give you a presentation on my internship topic development of low power thermal RGB imagery system for effective heat stress management in grapevines. Motivation for my project was that there has been a significant quality loss of grapes in 2021. As per Washington status, there is a 30% grape berry loss in 2021 in just the state of Washington. It is essential for us to make a heat and stress management grape quality testing system, as we don't have it due to inadequate sensing tools for reliable temperature monitoring. And we also need to develop a reliable sensing system for heat stress management in grapevines. For a little bit of background, this is Ranjan's project where he has made a crop physiology system using a Raspberry Pi right here. He has used a FLIR Duo Lipton camera, which is right here, and he has used OpenCV and Python for processing. Let's just compare single board computer and microcontrollers briefly. A Raspberry Pi, which is a single board computer, has better computational power and is versatile and flexible, whereas a microcontroller like STM32 consumes very low power and is very good at heat management. The limitations of Raspberry Pi is that it overheats and uses a lot of power, whereas the limitation of STM32 is that it has lesser computational power. If we compare the power consumptions of both of them, the Raspberry Pi usually uses double the power than an STM32. Comparing the maximum operating temperature, the Raspberry Pi can go up to 70 degrees Celsius, whereas an STM32 can go up to 85 degrees Celsius. There is a picture of both of them just for reference. This is the overview of my CPSS using STM32. We have a camera sensing unit which uses OpenMV-H7 camera, which is an RGB camera, and a FLIR Lipton thermal camera. And in the processing unit, we have an STM32 M7 microprocessor, and we have used YOLO V8 and Python for processing the images. And for the communication, we have used Wi-Fi that was inbuilt in the STM32, and then we have used LoRaWAN for long-range wide area network. This is how my proposed system looks like. We have an OpenMV camera which looks like this, and a FLIR Lipton thermal camera which looks like this in the camera sensing unit, and then we have an STM32 Cortex M7 chip which looks like this, and then we have YOLO V8 and Python for the processing of the data. Let us now discuss how the workflow of the system looks like. The system wakes up every 5 minutes and then the RTC time is synced. Then after the time is synced, the RGB camera clicks a picture which is then sent to the YOLO V8 for instant segmentation of canopies and berries. After that, we generate a mask of size 160 by 120. This is because we have the 160-120 size for thermal camera. Then the thermal camera takes a picture and then we have an overlay of both the pictures and the mask. Then we calculate the berry and the canopy temperature and then transfer it to the cloud using LoRaWAN and Wi-Fi. And then the system sleeps for 5 minutes, and after 5 minutes the circle continues, and we have a data for the images every 5 minutes. Let's move on to the results. There are quite a lot of slides for the results. Let's see how they look like. First result slide is for the model performance. Let us first understand what is precision and recall. When the system says something is true, precision is how often it is actually true. And recall is when something really happens, recall tells us how often the system notices it. Let us understand what is box and mask first. Let us see to this picture in the corner. This is not related to my project, but it is just for the explanation of what is a mask and what is a box. So the rectangle you see here around the car is the box. So the box percentage written in the slide here basically represents this box. And the shaded area around this car is the mask of this car. So the mask percentage actually tells this area around the grape. So the precision for the box percentage is 82.4, whereas for the mask is 81.3. The recall for the same is 81.2, for the mask is 77.4. The MAP, so what is MAP? MAP stands for mean average precision at the threshold of 50, which is 87.3 for box, and mask has 84.5. So after the model performance of the YOLO V8, we have some training and validation graphs. On the left-hand side, we have seg loss versus the epochs over training and validation. Seg loss basically means segmentation loss, which actually tells us the measure of how accurately a model labels each pixel in an image. And the lowering graph on the both the graphs shows that how the loss is reduced over the period of training and validation. On the right hand side, we have DFL, which stands for distribution focal loss. This actually helps a model make more accurate guesses about the exact location of objects in an image. So this slide actually shows the predicted output of the YOLO V8 that I trained. If you can see here, we have some confidence level around the bounding box and the mask inside it. So if you can see, the maximum values some ranges somewhere around 92% and the minimum is around 28%, where the grapes are not very visible. So you can actually see the masks and the boxes both in the image right here with the confidence level of the grape detection. Let's move away from the YOLO V8 and other machine learning model that we've trained. Let's move on to the power consumption of the STM32. If you can see the straight line before and after this spike, it actually represents the idle state of the STM32, and this spike actually shows when the data is transferred, when that workflow is actually happening. So if we compare the power consumption of a Raspberry Pi and a STM32 in idle state, the Raspberry Pi actually takes 0.6 amperes, whereas the STM32 only took 0.0035 amperes, where this line is straight and there is no data transfer. Whereas the maximum power consumption of data transfer state for a Raspberry Pi is 0.75 amperes, whereas for STM32 it is only 20.28 amperes. So we have reduced the power by a lot, and it is a great achievement for the project that I was doing. Let's talk about the inference time of the model and the STM32. This on the right hand side is a real-time image. It is not very clear because we did not have a lot of RAM. These circled or marked objects are actually the grapes inside. This one is also grape, which is not very clear. So the TA here means that the ambient temperature, the temperature of the object, the minimum and the maximum temperature are 23 and 35 that are available. So the inference time of the model was 211 milliseconds, which is very less. And the available RAM that we used was 747.5 kilobytes, which is not a lot. And the canopy temperature according to this image is 35.59. The minimum temperature that the camera can go to at that point of time is 23.34, and the maximum temperature is 35.5. I would say that we successfully deployed edge computing on OpenMV and STM32. We achieved a 50% reduction in power usage, and we improved the reliability and stability by reducing the operational temperatures of the CPSS system. We also successfully implemented long-range sensing network using LoRaWAN technology. For future works, we definitely need more field testing. We need to conduct a network connectivity and data reliability test. We also need to optimize the system using crop stress indices. We also need to make a device that is a portable, user-friendly agricultural device, and we also need to integrate that device with existing agricultural monitoring systems so that it is easy to use. At the end, I would like to thank Dr. Lavkot to guide me and Shrikant Gorthi to help me a lot in this project, and Agate Institute for definitely giving me this chance, and also the CPAS lab members who helped me a lot during this and motivated me a lot during this whole time. And I really like the environment of the CPAS lab. Thank you, and that was all from my side. I'm open to any questions that you have, and I'll be happy to answer them. Thank you so much.